Chapter 7, Vector Spaces. The last chapter, the very last chapter. This is where we will have the results of the first 6 chapters together and extend them to a more general framework, not limiting to Rn. So first we will talk about what a vector space is and their subspaces. In the first 6 chapters, we talked about Rn, and each vector in Rn is an n-tuple like this, v1 to vn, and this is what the vectors in Rn look like. Here we would like to extend the results in chapter 1 to 6 to more general case. And this set here is no longer Rn. It's something that we call vector space, which we will define in just a little bit. And the elements of a vector space, we still use the notation v on the bar as before, and we still call them vectors. But these vectors now in this vector space, they can be actually vectors, but they can also be matrices and they could be functions. We will see examples along the way. First thing first, a vector space. What is a vector space? Vector space, we will use the abbreviation VS for vector space. A vector space is a real set V on which 2 operations called vector addition and scalar multiplications are defined. So it's not just a set, it's a set with 2 operations on which 2 operations are defined. So whenever we talked about a vector space, we need a set and we need the associated operations. These 2 operations are called vector addition and scalar multiplications, and they are defined so that for UVW vectors in V and any scalars A and B, the sum U plus V and the scalar multiples, we scale U by, this is scalar A, they are unique elements of V. They are unique elements of V, and such that the following axioms holds. And there are 8 of them, 8 axioms. And here are the axioms of a vector space. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. Let's look at each one of them in detail. First of all, U plus V is the sum of U and V is the same as the sum of V and U. For the second one, if we have the sum of U and V and then the sum with, and we sum it up with the W, this is the same as summing up V and W first, and then U is a sum with this is sum. So these 2 are the same. And there exists an element, they use the notation 0, and we call it the 0 vector, such that U plus the 0 vector is U. For any U, there exists an element. This is called the additive inverse of U, and we use the notation of U with a minus sign in between, in front. This is called additive inverse of U, and such that the sum of U and its additive inverse is the 0 vector, and this 0 vector is this one, is this 0 vector. The scale multiple of U by 1 is U. Scale U by the product AB It's the same as this vector. First we scale u by b, and then scaled this vector by a. If we sum up u and v and scale by a, it's the same as the sum of the scale multiples of u and v. If we sum up ab and then scale u by this scalar, it's the same as the sum of au plus bu. The elements in V, we call them vectors, as we would with Rn. So now we have defined a vector space that is a set with two operations, and those two operations satisfy these 8 axioms of a vector space. For now, it would be very helpful if we throw away everything that we had to learn before about calculations, about vectors and matrices, and to concentrate on these 8 axioms of a vector space that are given in front of us. And you will see why I say this in just a little bit. Now let's ask some questions. What would be the sum of a 0 and u vector? Let's go back to the axioms and see what we can find. The axioms say something about u and the 0 vector, but it says nothing of a 0 vector and u, right? Can we switch the order? This is u plus 0, right? But this is 0 plus u. Can we make it equal to u plus 0? Which axiom may help us? Which one of the axiom can help us to switch the order? This one can help us do that, right? By the first axiom, we can switch the order. 0 plus u is the same as u plus 0 by the first axiom. And what is u plus 0? And u plus 0 is u. So u plus 0 is u by the third axiom. So this is u. Another question. What if we scale the 0 vector by 2? Do we still get the 0 vector? Let's go back to the axioms and see which axiom may help us in this case. Well, which axiom might be helpful in this case? It says that if we scale a vector u by 1, we still get u, right? So we know if we scale the 0 vector by 1, we get the 0 vector. This is the fifth axiom. But what about 2? What do we know about 2? 2 times the 0 vector. Which axiom might be helpful in this case? Well, we do have a plus b. Scale u by the sum a plus b, we get this, right? So let's try to see if this axiom will help us. We know 2 can be written as 1 plus 1. So this is fine. And now we see the eighth axiom seems to be helpful. So we get 1, the 0 vector scale by 1, the 0 vector scale by 1, and we know what this is, right? We get 0 vector plus 0 vector. And what is 0 vector plus 0 vector? we know u plus 0 vector is u. So if we treat this vector as u, then we get the 0 vector. This is by the third axiom. So here we go to the 0 vector scale by 2 times is the 0 vector. How about the 0 vector scale by 0? Well, it's so intuitively true that it's the same as the 0 vector, right? But again, we need to prove it. We will leave this as an exercise. A very useful example of vector space is the function space. This is actually a vector space of functions. Fs, this is a calligraphic F. S, be the set of all functions from S to R. S is this S here. And S is a non-empty set. So it's the collection of all functions with the domain and codomain S and R. Before we see why function space is a vector space, let's recall the following terms for functions, where we have sum, we have scalar multiple, and we have equal. Well, two functions f and g are called equal. We say they are equal if f of t is the same as g of t for every t in S. And the sum, f plus g, is defined as like this. This function, this sum function, is defined like this. F plus g of t is f of t plus g of t for all t in S. And the scalar multiple af, we scale f by a, is defined like this. This is function af of t is a times f of t for all t in S. And we define the 0 function. It's equal to 0 for all t in S. And for any f in this set, the function, we put a minus sign in front, is defined as, this function is defined as minus ft for all t in S. For a vector space, we need to have the 0 vector. And it seems here we have a good candidate for the 0 vector, right? What is it? This 0 function seems to be a good candidate for the 0 vector. And that's indeed the case. As we will see, this is the 0 vector when we view the function space as a vector space. And for a vector space, we also need to have additive inverse for any vector in a vector space. And we also have an additive inverse quite ready here, right? That would be this function here. One question, what would be f plus this function here, minus f? By definition, when we sum up two functions, the sum function is like so. So we have f of t plus minus f of t, and this from what we have up there is f of t minus f of t, and we get 0 of t. An example, suppose we have s is equal to r and f and g are functions in f of r, and f of t is t, g of t is t squared. Let's look at the sum. The sum of f of g would be this function, and that will simply be the sum of t plus t squared. And if we scale f by 3, this is 3f function would be equal to 3 times f of t, which is t, so 3t. And this minus f function is defined as minus f of t is equal to minus 1 times f of t, so it becomes minus t. Theorem 7.1 says this function space that we have seen just a bit ago is a vector space. To verify that it's a vector space, we will go through the 8 axioms and see if the sum and scalar multiple that we have so defined for function space satisfy the 8 axioms of a vector space. Here we will do the proof for A1, A3, and A7 and leave the rest as exercises. So for A1, we need to show that the sum of f and g is the same as the sum of g and f, and there exists a zero vector, so that the sum of f and the zero vector is the same as f itself. Here we will use the notation of vector and function interchangeably with the understanding that f function is a vector here. And A7, if we scale the sum, it's the same as the sum of the scale multiples. So first, the sum function f plus g, by definition, it's the same as f of t plus g of t. We know this from D2. D2 is what we have here for function space. This is the same as g plus f, and then again, this is the same as the sum function g plus f of t. Now we want to show there's a zero vector. F plus 0, the sum function is f of t plus 0 of t, and this is 0 for all t, so this is the same as f of t. So we can treat the zero function as the zero vector. To verify that it satisfies the 7th axiom, we need to show this. So we want to show a sum f plus g of t by D3. We know if we scale a function like this, it's the same as this one. So we can pour out a. It's the same as a bracket and the sum function f plus g. And by definition of sum function, we get f of t plus g of t. This is D2. And this is the same as af plus ag. And by D3 again, we get this is af of t plus ag of t. So this is af plus ag of t. And this is D2 again. A very important class of functions is the class of polynomials. There's one example in the textbook. P is the set of all polynomials. Px is equal to a0 plus a1x to an xn, and n is a non-negative integer, and all these coefficients a0 to an are scalars. And P is the set of all polynomials of this form. And we will leave example 3 of the textbook in 7.1 as a reading assignment. Theorem 7.2 gives some very useful properties of a vector space, which may not be obvious from the definition. V is a vector space, as we have defined earlier. For vectors u, v, w in the vector space and any scalar a, the followings are true. If u plus w is the same as v plus w, then u is the same as v. And this means we can cancel off w on both sides. This is called the Rai Cancellation Law. This algebraic manipulation is that something we took for granted before, but now here it requires a proof. And B is the opposite, the other way around. W is put in front, and then we can also cancel W off, and again use the same as V. This is called left cancellation law. C, the zero vector is unique. There's only one zero vector. There cannot be two. And each vector in V has exactly one additive inverse. There cannot be two. And if we scale a vector u by 0, we get the zero vector. And if we scale the zero vector by any scalar a, we still get the zero vector. And if we scale a v vector by -1, we get its additive inverse. H says that if we scale v by a scalar minus a, then this is the same as scaling the additive inverse of v. Scaling the additive inverse of v by a. And this is the same as the additive inverse of AV. Let's start with the proof of the Rai cancellation law. So we have u plus w equal to v plus w. What would be helpful to get us u equal to v? Let's add something to the two sides of this equation. What would be useful here? We can add the additive inverse of w to both sides. Then these two will cancel out. These two will give us the zero vector. Then we get u equal to v. The left cancellation law can be done in a similar manner. Let's show the zero vector is unique. So suppose that 0 prime is also a zero vector. And we know u plus zero vector is the zero vector. So because 0 prime is a zero vector, so 0 plus this 0 prime is the zero vector, right? But we also know that we can switch the order. So this is the same as 0 prime plus 0. So now 0, treating this 0 as the zero vector, then we get 0 prime. This means 0 is the same as 0 prime, and the zero vector is unique. We will show A, C, E, and G, I think, and leave the rest for exercise. For E, we want to show if we scale any vector by 0, we get the zero vector. We know scale u by zero vector is the same as scale u by 0 plus 0. So this is 0 plus u, 0 u, 0 u, u scale by 0 plus u scale by 0 by the 8th axiom. And 0 u, this is the same as 0 u plus the zero vector. And so we have this common term on both sides. And so now we can use which law to show the desired result. If we use left cancellation law, then we can cancel off these two terms, then we get what we want. G, we want to show that scaling V by -1 will give us the additive inverse of V. We know that the sum of V and additive inverse is a zero vector, right? So let's try to sum up V and this vector here. Then this is the same as V scaled by this sum, 1 plus -1. And this is V scaled by 0. And in E, we already know when a vector is scaled by 0, we still get the zero vector. So the result is the zero vector, and this shows that the sum of these two is indeed the zero vector. So this is the additive inverse of V. And why can we conclude that this is the additive inverse of V? Why it's not another vector? Because D says each vector in V has exactly one additive inverse. So if we have shown D, that means that there's only one vector that the sum, when we sum up V and its additive inverse, it's equal to the zero vector, and this additive inverse is unique. So this vector must be the additive inverse. The proof for the other items are left as exercises.